Question 3b, Part 1. Sketch the curve y equals ln x. Here is a sketch of the curve y equals ln x. Notice that it's a curve that's increasing at a decreasing rate. It's also asymptotic to the y-axis and has an x-intercept at x equals 1. Part 2. Use the trapezoidal rule with three function values to find an approximation to the integral of ln x dx from x equals 1 to x equals 3. We'll start by setting up the three function values needed for the trapezoidal rule. So we're starting off from x equals 1, ending up at x equals 3. So we need a point halfway between 1 and 3. So it's x equals 2. So the three function values are ln1, ln2, and ln3. Now our value of h is equal to 1. That's the distance between subsequent x values. So the integral of ln x dx from x equals 1 to x equals 3 using the trapezoidal rule is approximately equal to h over 2 or 1 over 2 times ln1 plus 2 times ln2 plus ln3 all in brackets. This is the extended form of the trapezoidal rule. So that's two applications done in one step. So evaluating this expression here, we end up with ln2 plus half ln3 or approximately 1.24245 and so on. Part 3. State whether the approximation found in Part 2 is greater than or less than the exact value of the integral of ln x dx from x equals 1 to x equals 3. Justify your answer. From the graph sketched in Part 1, the two trapezia lie under the curve y equals ln x from x equals 1 to x equals 3. Hence the approximation found in Part 2 is less than the exact value of the integral from x equals 1 to x equals 3 of ln x dx. Now, I've provided an alternative explanation using calculus and considering the concavity of the curve. Given y equals ln x, then the first derivative, y dash, is equal to 1 over x, and the second derivative, y double dash, is equal to negative 1 over x squared. Now, x squared is going to be positive for values of x greater than 0, so negative 1 over x squared will be negative for values of x greater than 0. Hence, the curve is concave down, which means the trapezoidal rule will underestimate the exact value of the integral.